Today I am going to discuss a topic that is moment of force and its application, which is engineering mechanics module 1 part 3 ESME 301. Now, what is moment of a force? The product of the magnitude of a force and the perpendicular distance of the line of action of the force from a point is known as moment of a force about that point. So, in the figure 1 it is clear that the force F is acting and at a distance that is r, and the moment produced that is m, and r and F, these two are mutually perpendicular. Now, moment of a force about a point is the measure of, so the moment of the force about the point is measure of its rotational effect also. So, moment m of a point P about point O as shown in the figure 2 is given by m equals to P into d. So, here d is the perpendicular distance between the point of action of the force and the moment center. Now, we will discuss few problems related to moment. Now, problem 1. A man of weight 750 Newton stands on the middle rung of a ladder of weight 250 Newton as shown in the figure 3. Assuming a smooth wall at B and a stop at A to prevent slipping, find the reaction at A and B. That means, we have to calculate the reaction force at A and B, these 2 points. Now, total weight, that is W, it is nothing but weight of the man plus weight of the ladder. So, 750 plus 250 Newton, that is 1000 Newton. Now, RA and RB, these two are the reaction force. Now, first of all, we have to draw the free body diagram. So, that free body diagram that is shown in the figure 4. So, in the figure 4, there is a reaction at A has 2 components, that is, one is the horizontal component HA, another one is the vertical component, that is the VA. For equilibrium, the sum of the moment A is 0. So, if you see the figure 4, you can see that at point A, the HA and VA, the component of reaction force RA, and RB, as the RB is the horizontal, so there is no vertical component of point B. So, from the point C, the weight W is acting vertically downward. Now, summation of MA equals to 0, that means the total moment with respect to a particular point here A, point A is 0. So, RB into 30, that is the anti-clockwise moment. So, here anti-clockwise moment is considered as the positive moment, minus W into distance, that is the 15 by 2 equals to 0. So, finally, RB equals to W into 7.5 by 30. So, finally, the value of RB equals to 250 Newton. For equilibrium, so we know that summation of Fx equals to 0 and summation of Fy equals to 0. So, from the summation of Fx equals to 0, so HA minus RB equals to 0. From this, you can easily calculate the value of RB. So, RB equals to HA. So, that finally the value of RB equals to 250 Newton. Now, from summation of Fy equals to 0, Va minus W equals to 0. So, here Va equals to W, so that is 1000 Newton. So, finally, the reaction A is nothing but the root over of HA square minus plus Va square. So, Ra equals to 1030.78 Newton. So, reaction force at point A, that is Ra equals to 1030.78 Newton, and reaction force at point B, that is RB equals to 250 Newton. Now, the problem number 2, a rigid bar AB is supported in a vertical plane and carries a load 5 kilonewton at its free end as shown in this figure 5. Neglecting the weight of the bar itself, compute the magnitude of the tensile force induced in the horizontal string CD. Now, you have to calculate the force CD that is induced in the horizontal string. Now, T is the tensile force induced in the string CD. So, first of all, we have to draw the free body diagram of the system. So, that free body diagram is shown in the figure 6. For equilibrium, the sum of the moment at about point A must be 0 must be equal to 0. So, summation of m a equals to 0. So, 5 into b e, that is the anticlockwise moment, minus t into a d equals to 0. So, finally, t equals to 5 into b e by a d. So, t equals to 5 into L sin alpha by L by 2 cos alpha, and t equals to 10 tan alpha. So, the tensile force induced in the string T equals to 10 tan alpha kilonewton. Now, the problem 3, a horizontal prismatic bar AB of negligible weight and length L is hinged to a vertical wall at A and is supported at B by a tie rod BC that makes an angle alpha with the horizontal as shown in the figure 7. The vertical P can have any position along the bar as defined by the distance x from the wall. Determine the tensile force induced in the tie rod. Now, in this let T is the tensile tension induced in the tie rod. So, taking moment about point A, we can write that summation of m a equals to T sin alpha into L minus P x. So, we have considering A as the moment center. Now, from the equilibrium of the system, we know that summation of all the moment with respect to point A equals to 0. So, it is nothing but T sin alpha into L minus P x equals to 0. So, one moment is clockwise moment and another moment is anticlockwise moment. So, finally, T equals to P x by L sin alpha. So, the tension induced in the tie rod is nothing but P x by L sin alpha. Now, from the problem 4, the beam AB hinged at A and supported at B by a horizontal bar BC is subjected to the action of the force P applied as shown in the figure 8. Assuming ideal hinges means there is frictionless at A, B and C, find the force produced in the bar BC, neglect the weight of the bar. Now, the solution is the T equals to force produced in the bar BC and FBD of the beam that is shown in this figure. So, for the equilibrium of the beam, the sum of the moment about the point A must be equal to 0. So, summation of m a equals to 0. So, P cos 45 into L by 2 minus T into L equals to 0. So, finally, T equals to P cos 45 by 2. So, T equals to P into the value of cos 45 equals to 1 by 2 root 2, 1 by root 2. So, finally, the T equals to 0.354 P. So, the force produced in the bar BC, that is T equals to 0.35354 P. Okay, thank you.